Yesterday, we showed off a demonstration of the new real-time learning feature for Beta's language model. We call the ILM. And it's definitely a very impressive, very big milestone to dynamically improve your language model on the fly. However, I want to stress that the real importance, the real takeaway from that isn't that we can build this language model that can learn on the fly. It's a bit of a toy model, a little bit of a toy model, but it's very powerful. So if you want to put this in production, you definitely can, and it can handle complexity pretty well. Um, but it's specifically the set of techniques we used to improve both the speed and accuracy simultaneously, to the point that you can do this with any, not just a language model, with any AI. And I'm going to go into that in a little bit more detail, because usually there's a huge trade-off between with large language models, so LLMs, not ILM. One is that the training can take an inordinate amount of time for computing. Like I'm running this locally on my computer. If you look at the thing, this is running on my computer. I'm not running with any kind of GPUs. I'm not running or training models with like a data center. This is just everything's local. Um, and with large language models, you're dealing with running entire farms of compute units working on a language model to improve it over the period of, I haven't been keeping up, but like of weeks, days, weeks, months worth of compute time to keep doing this. And this isn't done necessarily at once. This is being done continually to improve the models. Um, and you have this trifecta of like you need an inordinate amount of training data, of compute time, and then you have some degree of quality you get from that. In theory, as you add more training data, as you add more time doing your training, the quality should go up. Although you start getting into diminishing returns. And what I'm demonstrating is like, okay, there's some techniques that allow you to you do not have to necessarily compromise. You can improve the accuracy while decreasing the speed at the same time, or decreasing the amount of time to train these models. And the particular technique that was behind this real-time learning that we develop is using expectations of a model. And I'm going to go do a little bit more depth in this. I'm using expectations as feedback. Um, so in this instance, specifically for the language model, as the user's talking to the model, it's talking to beta. Beta has a certain set of expectations given its training data about what the user is going to say at any given point in time. And it's when the user says something that the model doesn't expect, there's a violation of those expectations. That gives you a key insight. That gives not just me as a developer, but Beta AI as the AI is running, critical insight about what it needs to change to best match those expectations. And this is one of my biggest gripes against deep learning models, which is the underpinning of a lot of current modern AIs. It doesn't do that very well at all. It's just like your expectations are, I've got 9 billion parameters, and the calculations in those parameters are such that when you give me this prompt, I'll get this output, but I can't tell you anything more than that. That's why we don't use. We did play around with deep learning in beta for a little bit, but we eventually threw that away. We have something else called a characteristic engine. That's a bit different. It's characteristics, kind of an analog to a parameter in a deep learning model, but that's a whole different ballgame that I can go in for hours talking about. But specifically, the problem that we're looking at is saying, okay, as you're doing actions, you've already trained the AI at some point to do something well. Unless you're starting from scratch, in which case you're teaching it basic stuff. And when you're teaching an AI to do a task, you're asking it, to characterize something, to make a decision, to take an action, to spit something out. And there's something called a search space, which is all the ways an AI can accomplish a task, right or wrong. And the name of the game is to get that search space down as much as possible. And if you have certain expectations about when an AI is trying to do something, that can massively narrow it down. Because you say, okay, the AI says, okay, I need you to do task. It's step A, B, or C. Parsing language, responding to a user, performing a task, and it has already been trained on to do it before. But then now we have a slightly new task. There's some new thing in the environment. So this is out in production. This is out live when it's doing this, and something in step B fails. And normally, if you have deep learning, it's like, oh, it just fails. Whereas if you have expectations, you say, okay, step A, when I complete step A, I have some measure of success that's given for any AI. Did I complete the task? Did I complete the task successfully or not? But there's also expectations that I've learned that if I complete a task a certain way, certain things are going to happen. Did I do this for step A in this specific case? Yeah, all those expectations held. There might be a few like, okay, it's a little bit statistical. Like someone was like, 99% of the time it's this, but sometimes, there's this factor in the environment that's sometimes this. And, as an AI, it can be just random. It could be the weather for all we know. But step B is like, step B, we're told we failed. Well, what are the expectations that we've learned over time? The AI itself is built up about what it happens when it does that. Well, step B, let's say this, putting a package on a conveyor belt. One of our expectations is that the package, as soon as it goes, it starts moving. We detect that it moves. It's not necessarily a success metric. It's just something we've noticed over time as an AI. And when we did that, we didn't get this feedback. So something about placing down on the conveyor belt and step B and whatever this is doing failed. So then instead of like figuring out where in this giant model of the world that's billions of parameters, there's only a couple of parameters that could have affected that. Go look at what was specific about that. And worst comes to worst, if the AI can't figure that out, it can always have a human look at it. It's like, okay, there's 3 different things that could have happened. Maybe I just didn't train the AI enough. Or the AI says, hey, there was this other brand new factor I've never seen before that also happened. Let's say a cat jumped up. And so when I placed it down, the cat knocked it over. Now you have new training data. If you see a cat, you need to be more careful, call for help, whatever. That's outside the scope of this conversation. But now you're starting to talk about AI that can learn very quickly on the fly. And a quick demonstration of this, if I go through, talking about when I'm talking about actions apply also to language models. So beta AI, the core AI is actually built on actions and decisions. So for the language model, our action is saying we're making some assertion that when the user says something, the user is making assertions about what they want to see in the world. So when the user says, please open up the window, the language model is just converting that into saying user wants state of window to be open as opposed to closed. So if we look at this, this is just, some example records or example, chat conversations I've been having, testing this out. And this action state table is just an example of certain expectations it has of the user. Now this is a bit technical, but what it's asking for is saying, I'm expecting at this given point in the conversation with the user that they're going to give me information about, the length or subject of a video they want to see. And we know there's not that. So if there's a mistake or if there's an error, the AI knows I need to look at whatever happened here to fix that. And then we can use that information. So when the user says something similar to length or subject, and the AI kind of parse it and say, wait, is this close enough that I think they actually said it? I just don't, my language model isn't sophisticated enough to parse it. And then I'm going to go figure out backwards what the training data was that would have fixed that. And that's what I was showing off yesterday. And that was how I was doing this real-time thing. And the nice thing is this technique scales very well. Because again, a lot of this is like database query stuff. So we just have to figure out okay, what's the high priority thing at this given point in the conversation, because we're computing this very quickly. And these are all computed in a graph. So if, this action state can be a very huge graph, but we're only computing the part of the graph that is active at any given point in time. So there can be stuff about talking about, filing taxes. But if the user never talked about taxes in the first place, this would all be 0. So then you don't have to worry about searching through that or dealing with that. So the final takeaway and conclusion is this technique of making the expectations about what the AI wants to see in the world when it makes a certain decision, action, even has nothing to do with its meaning as objective at that point in time, is really important because you can use that later on in the training or feedback. And if you do it right, you can do, language learning on the fly as opposed to taking weeks and, thousands of GPUs running over days nonstop to do that. Where you're spending, you're wasting millions of dollars and weeks of people's time trying to do that when you can do that in real time just fine.